In the previous video, we have solved the minors and cofactors of the entries of a matrix. The reason for that is for the definition of the determinant of a square matrix. The definition says if A is a square matrix of order n greater than or equal to 2, then the determinant of A is the sum of the entries in the first row multiplied by their respective cofactors. In symbols, that would be the determinant of A will be the summation of A sub ij times C sub ij, j equals 1 to n. That would mean that we have the product, or the sum rather, A sub 1 1 times its cofactor, plus A sub 1 2 times its cofactor, plus until the last entry in the first row times its cofactor. Now, take note that this definition is for square matrices rather, of order n greater than 2. If your matrix is of order 1, the determinant of that matrix is simply the entry of the matrix itself. Now, this definition as well leads to the initial formula that was given to find the determinant of a 2 by 2 matrix. So, let's use that definition to find the determinant of the following matrices. So, pause the video and try to see if you'll be able to find the determinant of matrix A. Alright, so we are asked to find the determinant of matrix A. For matrix A, that would mean that the determinant of A, there you go, would be this one, 0 multiplied to its cofactor, plus 2 multiplied to its cofactor, plus 1 multiplied to its cofactor. And since this is 0, this gets cancelled out, so we only need to compute for this one. Now, let's try to compute C sub 1, 2. We know that C sub 1, 2 is equal to negative 1 raised to 1 plus 2 of M sub 1, 2. So let's look for that M sub 1, 2. M sub 1, 2 is the minor, the determinant of the matrix when we remove the first row, the second column. So that meant this is actually negative 1 raised to 1 plus 2 multiplied to the determinant of the 2 by 2 matrix, 3, 4, 2, 1, which we can actually rewrite as negative 1, this 1 plus 2 multiplied to this product minus this product. 3 times 1 minus 2 times 4. This will be negative 1 raised to 3. Then we'll have 3 minus 8. And we know that this is actually negative 1 raised to 3 times negative 5. So this becomes negative 1. Negative 1 times negative 5 is positive 5. So we now have our C sub 1, 2. Let's now look for our C sub, oops, not 1, 2. This is supposedly 1, 3. So let's look for that C sub 1, 3, which is actually negative 1 raised to 1 plus 3 to the multiply to the minor 1, 3. So that would mean, let me erase this 2. I'm looking for negative 1 raised to 1 plus 3 multiplied to the determinant of that one there. We remove that, so we'll be left with 3, negative 1, 4, 0. That means, let's just bring down that panel down here. There you go. We're now going to have negative 1. 1 plus 3 is 4. Multiplied to 3 times 0 minus negative 1 times 4. And simplifying this, we'll have here negative 1 raised to 4 is just 1. So we'll be left with this one here of 0 minus negative 4, which is positive 4. So now we have the two values that we need. So therefore, the determinant of A, we can write it here. Determinant of A would be equal to 2 times 5 plus 1 There you go. 1 times 4, which would be equal to 10 plus 4, which is 14. So therefore, the determinant of A is 14. Now, before we solve letter B, or the matrix B rather, we have to look at our matrix. As you can see, if we're going to find the determinant of this one using our definition, we would have to find the sum of this one and its factors. Now, if we try to find the minor, say for example the minor sub 1, we're going to be left with a 3 by 3, and then we still have to go back on how we then again find the minor. Because remember, the only formula that we have is for a 2 by 2 matrix. So we will find a lot of minors. However, as you can see, we had this column here with all zeros. If only we can use the definition for any row or any column, it would work, because it would be easier to find for rows with zeros, just like what we had here. Our first entry is 0, which helped us reduce our time of solving. Now, there is this process known as the cofactor expansion. This is a theorem that says let A be a square matrix of order n. Then the determinant of A is given by these, which would mean that we can actually choose any row or any column of choice when we do our cofactor expansion. Because although the determinant is defined as an expansion by the cofactors in the first row, it can actually be shown that the determinant can be evaluated by expanding in any row or any column. This theorem is also known as the Laplace expansion of a determinant after the French mathematician Pierre-Simon de Laplace. So cofactor expansion can be done in any row and in any column. So that would mean it would give us the freedom to choose any row or any column of choice. Which, if we're going to find the determinant of B here, determinant of B, it's better to choose to expand, to do the cofactor expansion rather, here in the third column. Because all we need to do is multiply 3 rather to its cofactor, that would be 1, 3, and the rest are zeros. To show the cofactor expansion for matrix B, let's go to the next video.